gonna skip this ad. And then I'm streaming. Hey, I'm streaming. How's it going? I was streaming just a second ago, but I didn't have my mic turned on. I'm talking a little bit about what's going to happen for the exam, and while I'm talking, I'm typing this up into Blackboard so that people who aren't watching this part of the video can also have all the information. I want to have exam 1 this Monday from 4 to 6. If you can't do 4 to 6, that's fine, but let me know as soon as possible. I think that's when the class would have been scheduled for. I don't know what it said when you signed up for the class. Like, you're not obligated to be available 4 to 6, but I'm guessing that's a time that most people are. I like having everyone do it at the same time, so I know no one's passing other people. Like, if people are doing it at different times, then I'm writing different versions of the exam, which is a hassle, but it gives me more practice exams to give out next time. There's a practice exam posted. Your exam will be about as difficult as it. Yeah, so hopefully you're free from 4 to 6. If you're not, let me know now and we can figure something out. Maybe we can move everyone around. The exam will be posted at... I said posted at 2, not at 2. That's my other classes, 2 to 4. Your class is 4 to 6. The exam will be posted at 4. You take paper, you do the problems. Try to put each problem on its own sheet, just for organizational purposes. Like, every year I have a student who starts problem 3 on the bottom half of problem 2. Just wait till you're done with problem 2 before you know if you have enough space. Like, give yourself a new sheet. This is assuming you have enough paper to go around. I don't know how much paper you have in your house. You need paper for the class. It's due at 4, so before 4, take pictures of your work and email them to my Gmail address, yinks.math@gmail.com. This is a Gmail I just use for receiving homework. It's a huge... Grading online stuff is a hassle wherever, but Gmail makes it way easier than the other ones. I'll email you comments on your grades back and whenever I'm done grading. And on Tuesday we'll start with sequences and series. If you have a fancy scanner you want to use, feel free to use it, but a good smartphone today is just as good as a scanner, or, you know, it doesn't need to be good. I'm not making a wallpaper out of your exam. A cell phone picture, if you get decent lighting, is just fine. Try and stand somewhere where your shadow's not on the paper. Is this all clear? Are there questions about the policy? Let me know if you have any questions. Submit. I know I asked you guys to be available to do some live interactive math class stuff on Wednesday and Thursday, but I am almost out of stuff to say. If you guys are interested, I can post the problems that I would post for a integration bee, which are basically just typical problem type stuff, and you guys can do the problems and I can look at your work. The thing I was going to do, like, all I have to do is do a bunch of problems, and I'm going to do a bunch of problems. And then whenever I'm done doing problems, I was going to go through the practice exam. I would encourage you not to watch the practice exam right now if you're watching live. Save it until you've done the regular exam. I said I was going to post solutions to the homework problems because I thought I had them, but I can't find them. I'm going to go through my computer some more and see if they exist. If I don't have them, I can start making them and post them, but I don't know if I'll be done by Monday. I'm seriously confused about why I thought I had that. Cool. Is anyone watching live? Do you guys want to do a problem and email it to me? What do you feel like doing? You got ideas? Is anybody there? Where do I check if... concurrent viewer is 1, but I never know if that's me. I guess I'm going to post a problem, and then I'll wait a minute. Oh, I posted a problem at the end of last time. Why don't I start by seeing if I can do that? That's not it. Do I still have that window open? No, that's not Cal 2. That's not Cal 2. This is Cal 2, but this is the bottom of this document. Oh. Yeah, that's the last lecture thing. Yeah, that's not it either. Unless... No, that's not it. Let's do... Let me see if I can do that hard problem from last time. The one I said was funny. Let's see if I can get this right on the first try. The goal was to integrate from 0 to 1. The bottom was x squared plus 1, and the top was x to the 4th, 1 minus x to the 4th, dx. There's nothing deep about this problem. It's a partial fractions thing, but there's only one part on bottom. So, like the split, the partial fractions part doesn't matter. All that we need to do is the long division. Let's do some long division. X to the 4th, 1 minus x to the 4th is x to the 4th times, you take that 4th power, you get 1, 4, 6, 4, 1, oh, I missed the squared. I missed the power of 2. 3 plus x to the 4th. So this is x to the 8 minus 4x to the 7 plus 6x to the 6 minus 4x to the 5th plus 1x to the 4th. Okay. So if I divide all that by x squared plus 1, I'm doing a big long division. I guess it's nice to have an excuse to write out a nice long division. I'm going to copy this to a new page, because this is going to be massive. We draw our shepherd's hook, shepherd's crook. I remember learning in elementary school that the symbol you use for long division with this thing here is called a shepherd's crook, or possibly a shepherd's hook. Minus 4x to the 5th plus x to the 4th, 0x cubed, 0x squared, 0x, 0. We're dividing this by x squared plus 0x plus 1. This is functioning like a 3-digit number that we're dividing by. We start with first digit divided by first digit. x8 over x2 is x to the 6. Multiply and get x to the 8 plus x to the 6. Subtract. I get negative 4x to the 7. 6 minus 1 is positive 5x to the 6 minus 4x to the 5th. Divide. First digit by first digit. Negative 4x to the 7 divided by x squared is negative 4x to the 5th. I'm putting it on the x to the 5th column. Multiply this by x squared plus 1, and I get negative 4x to the 7th. Plus 1 times negative 4x to the 5th is negative 4x to the 5th. Subtract. That cancels and this cancels, and I'm left with 5x to the 6 plus x to the 4. Divide first digit by first digit. 5x to the 6 divided by x squared makes 5x to the 4. That's a 4. Multiply. 5x to the 4 times this stuff is 5x to the 6. 0 middle term. Plus 5x to the 4th. Subtract. 0 minus 0 cancels. X to the 4th minus 5x to the 4th is negative 4x to the 4th. Bring down the next term, which is 0. Negative 4x to the 4th divided by x squared makes negative 4x squared. We're skipping a digit. And if this was a numbers long division, we'd be putting a digit of 0 here. A digit of 0 in a polynomial is a term that's not there. You don't have to write it out. Negative 4x squared times all this stuff. I get negative 4x squared times x squared is negative 4x to the 4th. Middle term is nothing. Minus 4x squared. I need to bring down the 0x squared. Doesn't do anything. Let me double check my subtractions are going right. Yeah, I'm remembering to subtract and not add. Subtract that cancels, but there was never anything there. I'm left with positive 4x squared. 0x plus 0. Divide. 4x squared divided by x squared is 4. Multiply 4x squared plus 4. Subtract negative 4. is my remainder. So we divided and we found that x to the fourth, 1 minus x to the fourth, parentheses there, over x squared plus 1 looks like it's x to the 6 minus 4x to the 5th plus 5x to the 4th minus 4x squared plus 4 with a remainder of minus 4 over x squared plus 1. And our goal was to integrate this from 0 to 1. This is not a hard integral. Integral from 0 to 1 of this thing. I get the integral of x to the 6 is 1/7 x to the 7 minus 4/6 x to the 6 plus 5 over 5 x to the 5th minus 4 over 3 x cubed plus 4x minus the integral of that is 4 tangent inverse x plus a constant, or you don't need to put the plus c because now we're going to evaluate that from 0 to 1. Let's see what we get. When we plug in 0, we get 0, 0, 0, 0, 0, 0. Tangent inverse 0 is also 0. Plugging in 0 gives nothing. So we just need to plug in 1. I get 1/7 minus 4/6 is 2/3 plus 1 minus 4/3 plus 4. Oh, I can already see I've messed this up. Minus, plug in 1 here, you get 4 tangent inverse 1 is 4 pi over 4. Maybe I haven't messed this up. Yeah, I think these... Can I see where I'm... Yeah, this fraction's not canceling out like it's supposed to. I'm getting the 1/7. Oh, this is right. Okay, so I get 1/7. Plus 1 plus 4 is plus 5. Oh, this is working out perfectly. Minus 6/3. Minus 6/3 is minus 2 minus pi. 5 minus 2 is 3. I have 3 plus 1/7 minus pi. What's 3 1/7? 3 is 21 over 7 plus 1 over 7 is 22 over 7 minus pi. Hey, we did it right on the first try. I'm feeling very proud of myself. I feel like I've redeemed all my partial fractions mistakes that we made. We just worked out this integral. The integral from 0 to 1 of x to the 4th, 1 minus x to the 4th over x squared plus 1, and it turned out to be 22 over 7 minus pi. Why is this hilarious? Do you recognize this number 22 over 7? It's famous for being an approximation of pi. Math teachers know it as the thing they have to convince their students isn't actually equal to pi. We just found out, hey, what do I know about this function x to the 4th, 1 minus x to the 4th, x squared plus 1? Between 0 and 1, x is positive, 1 minus x is positive, x squared plus 1 is always positive. This is integral from 0 to 1 of a positive function, at least positive between 0 and 1. Well, it's always positive. We integrated something positive, and we got 22 over 7 minus pi. From that we can conclude 22 over 7 minus pi is positive. And in particular, if you weren't sure, pi turns out to be less than 22 over 7. We have just concluded by hand. In particular, it's not equal to 22 over 7, if you had someone who wasn't sure about that. This isn't a super complicated function. I think it's just hilarious that this integral turns out to be 22 over 7 minus pi. Anyway, that's that example that I told you about at the end of class last time. I didn't think I would get it right on the first try. I feel great. I feel invincible. You guys. I'm going to do some integrals. Is anybody watching? One who might be me. I can't tell if anyone's watching. I'm just going to do some integrals. These are some things I would have had out on the integration bee. 1 over x root x squared minus 4. How do I do this? I see that square root type of thing, and it makes me think about a trig substitution. Before I dive in with a trig substitution, it's worth checking, is there something easier? Like, could I just do the u substitution, u equals x minus 4? If that works, it's probably going to be easier. Let's actually try that. If I do u equals x squared minus 4, du needs to be 2x dx. What is that going to turn into? It's going to turn into... I wish I had a 2x up here. The 1/2 I can pull outside to cancel it, but the extra x I cannot. I should... Don't write on the original problem. Let's copy the problem to write this garbage onto. If I wanted to make the substitution work, I would change it. I would stick an x on top to be part of the du, stick an extra x on bottom because I'm not allowed to just put x's wherever I like, and put a 1/2 to cancel a 2 I put on top. The substitution will become 1/2 integral of 2x dx is now du. Square root x squared minus 4 becomes square root of u. What do I do with that x squared? I could solve for x, but that's overkill. X squared is u plus 4. Is this any better? I guess from this I might do the substitution v is the square root of u. U is v squared, so du is 2v dv. That'll get rid of the square root. What does this turn into? 1/2 integral of u is now v squared. Oh, du is now 2v dv. So u plus 4 becomes v squared plus 4, and the square root of u has become v. I can, well, actually, the v's cancel. The 2's cancel. I get the integral of 1 over u squared plus 4, or v squared plus 4 dv. This is just a tangent inverse type deal. This might be worth memorizing. I think the answer to this is 1/2 tangent inverse v over 2. Like, it's almost v squared plus 1. There's a baby substitution you can do to change this out. I never get that substitution right, though. Like, it's the thing you got to think about is I wish I could factor a 4 out of the bottom. If I factor the 4 out of the bottom, it becomes v over 2 squared plus 1. You factor a 4 out of this and it becomes 1/4 v squared plus 1 when the 4 is outside. So the 1/4 v squared is v over 2 squared. Do a substitution on a v over 2, you get a tangent inverse v over 2. You cancel a 1/2. One of these 1/4 is left over. Yeah, so this is the answer. And what was v? V was square root u. What was u? I think the answer is 1/2 tangent inverse square root x squared minus 4 over 2 dx. Not dx, plus c. It worked without a trig substitution. Let's do the trig substitution anyway. Hey, trig substitution's useful. We had a whole day of lecture on it, so... What's the substitution to use? I believe it's secant. Yeah, 2 secant theta. Then dx will be 2 secant tangent. And x squared minus 4 is going to be 4 secant squared minus 1 is 4 tangent squared theta. What does my integral turn into? X becomes 2 secant theta. X squared minus 4 is 4 tangent squared, so the square root of that is going to be 2 tangent. Technically 2 absolute value tangent, but we can cope with that. What's dx? Dx is 2 secant theta tangent theta. Oh man, this is way easier. Secants, tangents, 2's. We get 1/2 integral of 1. The integral of 1, you're always tempted to say x, but you didn't let me finish. It was the integral of 1 d theta is theta. What was theta? Theta is secant inverse x over 2. I guess secant inverse x over 2 is the same as tangent inverse x squared minus 4 over 2. That seems reasonable. I know there's a relationship between secant and tangent, which is going to make there be a relationship between secant inverse and tangent inverse. That's a thing you can check your answers on. Or a thing you can inspect later. Cool. Is there a secant do people use secant inverse? There's no secant inverse button on the calculator. Maybe it's bad form to use secant inverse at all. Maybe we should do cosine inverse instead. If secant theta is x over 2, that's the same as saying that cosine theta is 2 over x. Maybe it's better to use theta as cosine inverse 2 over x? I'm not sure. It feels bad form to use secant inverse when my calculator doesn't have a secant inverse button. But it is a function. I don't know. Let's do the integral of 1 over x squared x minus 4. This is begging for partial fractions. Do I see any trick to get around it? I don't think I do. Let's do a partial fraction decomposition of 1 over x squared x minus 4. You're going to be a over x, b over x squared, c over x minus 4. The cover-up trick can give me b and c, but it won't give me a. Maybe I'll do the cover-up trick and just treat that as a way to check my work. Mostly because I love the cover-up trick. Let's multiply by x minus 4, and then plug in x equals 4. I get c is 1 over 16. Let's multiply by x squared and plug in 0. Multiplying by x squared, plugging in 0, gives me that b is negative 1/4. I need a pencil, not a highlighter. I guess now I need an eraser. Now I need a pencil. B, what did I do? I plugged in 0. B is negative 1/4. I can plug those two things in and plug in any other point for x to get the a. That feels like it's starting to be more work than just doing it the right way. Let's multiply both sides by x squared x minus 4. We did a bunch of examples in class that got really gross. Hopefully you've done enough homework to know that the problems we actually do are not usually that bad. I sort of have to show the really hard ones so you know how to do the less hard ones. So you're prepared for the little things that can happen. I get a times x squared minus 4x plus b x minus 4 plus c x squared. I want to group these by powers of x. How many x squareds do I have? I have a plus c x squared. How many x's do I have? I have negative 4a plus b. What do I have for a constant? I have negative 4b. Oh, this is actually really easy to solve. I'm getting a plus c is the x squared coefficient is 0. I'm getting negative 4a plus b is my x coefficient is also 0. I'm getting negative 4b is my constant coefficient is 1. So b is negative 1/4. Cool. If b is negative 1/4, then negative 4a minus 1/4 equals 0. So negative 4a equals 1/4. So a is negative 1/16. And c is negative a is positive 1/16. Cool. The two we had earlier are confirmed. Check. So that integral is now the integral of a over x, b over x squared, c over x minus 4. And these are easy to do. Integral of 1 over x is natural log absolute value x. Integral of 1 over x squared is negative 1 over x. Integral of 1 over x minus 4 is natural log absolute value x minus 4, plus a constant. Cool. Let's do... Oh, I know a good one. Oh, have we done sine inverse? I think natural log of cosine x is a good one. What would you try? If you tried u equals cosine x, you just don't have a sine x out there. So you're going to have x as cosine inverse. You need to look up the derivative of cosine inverse to figure out what dx is. That sounds rough. Like, I think the only thing that jumps out to me is this is the integral of natural log something. The way we integrate natural log x is by parts, making sure to take the derivative of natural log. Derivative of natural log is nice because it doesn't have a log in it anymore. So I think that's the thing we got to do. Let's try parts. I want to do parts with u equals ln cosine x. dv is just 1 dx. du is going to be, what's the derivative of that? It's 1 over cosine x times sine x. What's v? V is the integral of that. It's x. This turns into the integral of x sine x over cosine x. Can we do that? I can rewrite that as x tangent x. Gross. Or I forgot the UV part. UV is x natural log cosine x minus this. So now I'm left hoping to integrate that. Okay, I know how to integrate x sine x or x cosine x. Those are both obvious parts problems where I would want to take the derivative of the x and integrate the other thing. But if I do that right now, that's going to be undoing the integral by parts we just did. It's going to take us back to our original problem, and it's going to take us back in the bad way. And I want to learn not to do that mistake. What else could I try? I can try a u substitution about cosine. That'll soak up the sine that's out there. But the x on the outside seems like it's going to make that bad. Let's give it a shot anyway. If I have u equals cosine x, du is negative sine x dx. I can make u positive and make u negative to soak up the negative here. And what's x? X is going to be cosine inverse u. Some of this gets nicer, but I get x log cosine x plus the integral of du over u times that x is cosine inverse u. Well, this I definitely want to do by parts to get rid of the cosine inverse by taking its derivative, but I think this is just a long way of taking us back to the original problem. Man, this is what I get for trying to make up a problem. I don't know how to do this. This doesn't seem like it's working. The obvious tricks aren't being useful. Maybe it was cosine of natural log x. I'm not going to try and figure that out. Yeah, it was. That's the one that is a nice parts problem. I'm going to give up on that one. Did anybody show up? I guess what I'm going to do now is go through the practice exam. If you're watching live, or if you're watching later... Oh, here's some problems I want to do. Not yet. Coming up soon. Oh, I like doing this one. I'm going to do the following 6 integrals. I'm going to integrate cosine x to the n, where n goes from -2 to +3. So this is 6 different problems. They're all just a different power of cosine. Let's start with -2. How do I integrate cosine x to the -2? Well, that's 1 over cosine squared x. That's secant squared x. What's the integral of secant squared x? That's right, it's tangent x. How about cosine x to the -1? That's 1 over cosine, that's secant. How do you integrate secant? I think this one is worth memorizing. It's natural log absolute value, secant plus tangent. There's ways around it, but they're all gross and weird. If you don't know how to do it by hand, make sure you also have memorized the integral of cosecant. It's the same as this, but with cosecant and cotangent and with a minus sign out front. All the codes are the same as the regulars, but code and with a minus sign. What's the integral of cosine x to the 0? It's unbelievably fun to give this problem to students on the integration bee and see how many of them forget that they know how to integrate 1. It's x. What's the integral of cosine x to the 1? Oh, that's the integral of cosine x. That's sine x. What's the integral of cosine x to the 2? We're integrating cosine squared. This is the one where you need that specific trig identity. Make sure you have that specific trig identity stuck into your head. The cosine squared is 1/2 plus cosine 2x over... Not cosine squared, cosine 2x over 2. Gross. It's the integral of 1/2. 1 plus cosine 2x. The integral of 1/2 is x over 2. The integral of cosine 2x over 2 is sine 2x over 2. And last up, what's the integral of cosine x cubed? This is an odd power. We like odd powers. When we see an odd power of sine or cosine, we pull off one of them to go with the dx. Putting it next to the dx is my memory trigger to say, aha, I want that to be d something. What should I make u? If I want du to be cosine x dx, u should be sine x. Du will be cosine x dx. If u is sine x, I just need to turn this cosine squared into sines. I can. That's 1 minus sine squared x cosine x dx. According to that substitution, that's the integral of 1 minus u squared du. That's u minus 1/3 u cubed. That makes it cosine x minus 1/3 cosine cubed x. Those are these powers of trig integrals. Okay, now I'm all out of problems to do. I'm going to go through this practice exam. If you're watching live or watching later, I recommend stopping. Go do the practice exam by yourself before you look at the answers. Like, the great thing about a practice exam is it gives you a chance to practice taking the exam. You might as well go full hog and give yourself, find out if 2 hours is enough time for you. See what is taking all your time. Get better at doing that stuff faster. I'm going to go through it now, just so that that's it. I'm probably not going to show up to lecture tomorrow unless people give me enough questions. I mean, feel free to ask questions. Ask as many questions as you want over the weekend. The exam will be Monday. I'll see you Monday, unless I see you sooner because you sent me questions. Feel free to send me questions. None of you guys ever send me homework questions, and it makes me concerned. I'm really glad to have done some problems yesterday and learned that some of you know how to do some problems. You are welcome to ask me questions. I'm getting paid for this. Get your money's worth. Like, cool. I'm going to start the practice exam. Stop watching. Come back when you've done it. Make sure you notice this is telling you to state the form of the partial fraction expansion. We don't need to actually find it. Go away, volume thingy. Why are you still... How do I make you... There. We don't need to actually find the partial fraction decomposition. We just need to state the form of it. There's a good chance you put a over x, b over x plus 1, c over x plus 1 squared, dx plus e over x squared minus 1, fx plus g over x squared minus 1 squared, h x plus I over x squared plus 4. But this is wrong. X squared minus 1 factors. Factoring by itself isn't an issue. The issue is that one of the factors is some more x plus 1's where they need to get grouped together. X squared minus 1 is x minus 1, x plus 1. It's squared, so these are squared. This becomes part of this as a power of 4, and you have to do this for the expansion to actually exist. The decomposition should have been a over x, b over x plus 1, c over x plus 1 squared, d over x plus 1 cubed, e over x plus 1 to the 4th, we have to count all the way up to 4, f over x minus 1, g over x minus 1 squared, and then hx plus I over x squared plus 4. There's the form of the decomposition. I'm not going to actually make you find this decomposition. This would be a nightmare. This would be 9 variables and 9 equations. Does the cover-up method get you anything? Cover-up method will get you this one, and this one, and this one. Yeah, that's not enough. Let's do number 2. This one isn't just find the form, this one is actually do the decomposition. I guess I keep calling that expansion, not decomposition. What's the form? The form is it's going to be I guess step 0, is the top smaller than the bottom? The top is linear, if we FOIL out the bottom it'll be cubic, yes, we are ready to go. This is a over x minus 2. I say ready to go, what I mean is we don't need to do the long division thing. Now bx plus c over x squared plus 4. And now, let's clear the fractions. Clear, 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 clear. I get that x plus 2 equals a x squared plus 1 plus bx plus c x minus 2. Can I start grouping these by powers of x yet? I should probably FOIL this out. Let's see if we can do it without FOILing that out in a separate step. I get ax squared. I get bx squared when I do that part of the FOILing on the right. How many x's do I get? This gives me none x's. This one gives me minus 2bx's, and I get a plus cx. What's my constant part? I get plus a is a constant term. I get minus 2c is a constant term. This is all supposed to be x plus 2. So the x squared coefficient is a plus b needs to be 0. The x coefficient is negative 2b plus c needs to be 1. And the constant coefficient is a minus 2c needs to be 2. I have 3 equations, 3 variables, not that bad. Let's see. The first one, a equals negative b, I can use to eliminate the a in the other 2 equations if I want. The middle one already doesn't have an a. If I change that a into a negative b, I get this. If I double the first equation, so this is saying times 2, that gives me negative 4b plus 2c equals 1. Leave the second equation alone, negative b minus 2c equals 2. Oh, when I double the first equation, that 1 should have been a 2. Add those up, negative 5b equals 4, b is negative 4/5. I did it that way to clear the c's and get b. Let's clear the b's and get c instead. Let's take the second equation and multiply it by negative 2. Multiplying the second equation by negative 2 gives me positive 2b plus 4c equals negative 4. The first equation says negative 2b plus c equals 1. Add those up, 5c equals negative 3, c equals negative 3/5. A was negative b, so a is 4/5. I think I have all the values. So our problem is turned into x plus 2 over x minus 2, x squared plus 4. The decomposition is 4/5 over x minus 2 plus bx plus c is negative 4/5 x plus c is negative 3/5 over x squared plus 4. Cool. Put a box around this. This problem didn't actually ask us to integrate it, so don't need to do the integral yet. Next problem. Evaluate this integral. This is an improper integral. Improper is the word for the fact that the integral is trying to go out to infinity. I'm going to follow instructions and grab a brand new sheet of paper for every problem I'm doing. It's really tempting to say the integral of that is x to the 1/4, divide by 1/4, evaluate that from 0 to 81. I'm not going to get a lot of points if I do that. The thing going on is the function is undefined at 0. This thing goes to infinity at 0. It's badly behaved at 0. The thing I'm proving I know how to do to get the points for this problem is rewrite this as a limit. As something goes to 0 from the right, integrate from that something to 81. Now, what's the integral of x to the negative 3/4? It's x to the 1/4, divide by a 4th. Evaluate that from alpha to 81. This is the limit as alpha goes to 0 from the right of 4th root of 81 is 3, so I get 12 minus 4 times the 4th root of alpha. 4th root is continuous at 0. I can take the 4th root of 0. I get 0. This is 12 minus 0 is 12. This integral converges and it's finite and it's just 12 and everything is fine. When it is finite, if I had done this, that would have given me the correct answer. It wouldn't have given me many points for the test, though. The point is rewriting the improper integral as a limit. We need to do 9 of these integrals. One of them is non-elementary. One of these integrals is impossible. Good news, you get to skip one of the 10 that's doable. Bad news, someone is sticking one of these in here. I should write more specific instructions on the test. I need to write myself a note to do that. But I'm only grading the first 9 you turn in. You need to tell me which 9 you're doing. Part of the thing you're being graded on is, do you know the things that you are doing is correct? So, yeah. I need to write way better instructions. I'll also have some take-home instructions with threats about cheating. Hey, don't cheat on this stuff. I know there's websites that'll do your integrals for you. I don't know if you know, it's super obvious when a student uses those, so, you know, don't do that. How do you integrate tangent squared? Let's not follow instructions. I do 2 to a page, because I know one of these is real fast. Number 4 is about what's the integral of tangent squared. There's many tricky ways to do this. The easy way is use a trig identity. What's tangent squared? It's secant squared minus 1. Is it secant squared plus 1? I can never... I used to always know this. Sine squared plus cosine squared is 1. Divide both sides by cosine squared. That gives you the other trig identities. So that says sine over cosine squared is tangent squared plus 1 equals secant squared. So tangent squared is secant squared x, not theta. We're not switching variables here. Minus 1. What's the integral of secant squared? It's tangent. What's the integral of 1? It's x plus a constant. Boom. Number 5. The integral of x minus 2 over x minus 1, x plus 3. This is a baby partial fraction. I'm saying baby. It's a real-life partial fraction. It's just a very easy one. This is one where the cover-up method does everything for you, so you don't have to do the whole writing thing. This is why it's listed separately from the other harder partial fraction thing. This is going to be a over x minus 1, b over x plus 3. If I multiply by x minus 1, plug in x equals 1, I get x equals 1 minus 2 over 1 plus 3 is negative 1/4. Let's try and clear the b. If I multiply by x minus 3 and then plug in negative 3, I'm going to get that b is, I'm plugging in negative 3. Negative 3 minus 2 is negative 5 over negative 3 minus 1 is negative 4. So b is 5/4. This decomposes as the integral of. Hey, if you're writing these problems out, you don't need to write out what you're doing for the cover-up trick. I've been writing it out because I'm trying to make something that you guys can understand. Just say the words cover-up to say where these numbers come from. You don't need to give more explanation than that. So now I'm integrating a over x minus 1, b over x plus 3. This is negative 1/4 over x minus 1, 5/4 over x plus 3. This is negative 1/4 natural log absolute value x minus 1 plus 5/4 natural log absolute value x plus 3 plus a constant. Cool. Let's do number 6 and 7. I should have said this in class. I'm getting it feels like I didn't talk about number 6 in class. There's a formula called product to sum that lets you change a product of cosines or sines into a sum of sines or cosines. And it kind of comes from taking the angle addition formulas for sine and cosine and turning them inside out or something. And if you memorize those, you can use those. I don't like memorizing those. Number 6 is something that you can also do integrating by parts twice. To me, integrating by parts twice is way better than memorizing that formula. If you're memorizing that formula, go for it, but you gotta actually memorize it. I'm gonna do this by parts twice, because that's how I would do it if I had a test. Integral of cosine 12x, cosine 3x. I'm gonna let u be, let's make it the 12. dv is going to be the other one, cosine 3x. So du is negative 12 sine 12x dx. And v is the integral of this is negative 1/3, no, positive 1/3 sine 3x. Integrating cosine gives a positive sign, differentiating it gives a negative. So this integral, which I'm going to call I in a second, is uv 1/3 sine 3x cosine 12x minus the integral of v du. v du is going to be a sine 3x and a sine 12x, and I have a 1/3 and a 12 and a negative. The negative will cancel here. 1/3 of 12 is 4. This is my new thing. I'm going to do parts again. I want to make sure I'm moving in a forward direction. If I let u be the thing that came from the old v, if I let u be the sine 3x, I'm going to undo the last parts. I don't want to undo the last parts. I want to keep moving forward. I want to let u be the thing that came from the old u. U is going to be sine 12x. So dv is going to be the 4 sine 3x dx. Du is the derivative of that is 12 cosine 12x dx. V is going to be the integral of sine is negative cosine. Gotta divide by 3. I could put plus a constant there. There's probably not a reason to. So I get this equals 1/3 sine 3x cosine 12x plus uv is sine 12x times negative 4/3 cosine 3x minus the integral of v du. The minus is going to cancel with that minus. 12 times 4/3 is 16 cosine 3x cosine 12x dx. And this right here is the original problem, but with a 16 on it. So my original problem equals that function plus 16 times itself. Let's subtract 16 of the original problem from both sides. I get negative 15 of the original problem is that mess. So my integral is that divided by negative 15. I need to take this and divide it by negative 15. I get negative 1 over 45 sine 3x cosine 12x plus, now it's positive 4 over 45 sine 12x cosine 3x plus a constant. It's the kind of problem where I would feel good to take a derivative and check that it worked, but probably in a 2-hour exam I don't have time for that. Let's try number 7. X cubed over 1 plus 4x squared. Inside a square root. Inside a square root. Trig substitution is the obvious thing to do. It's probably what we're thinking about. Is it worth trying to do a u substitution? U equals 1 plus 4x squared. I don't see just an x on top, so it's not the slam dunk perfect kind of substitution. I could pull off one of those x's and I'd have an x squared, which would almost be u minus 1. I could turn this into u minus 1 over the square root of u, which would be doable with the power rule splitting that up. Yes, the u substitution would work, but it would be tricky. I'm going to do this with a trig substitution, because that's the trickier trick that you need to know how to do. This is 1 plus blank squared. The thing that is squared is 2x. I want to let 2x be tangent theta, because then 4x squared is going to be tangent squared theta, and 4x squared plus 1 is going to be tangent squared theta plus 1 is going to be secant squared theta. So the square root of 4x squared plus 1 is going to be the square root of tangent squared plus 1 is going to be that, is going to be secant theta. It's going to be absolute value secant theta, but I'm not going to deal with the absolute values. If 2x is tangent theta, then 2 dx is going to be secant squared theta d theta. I wish I had a 2. I can put 1 if I put a 1/2. This equals 1/2 integral. X cubed is going to be 1/8 tangent cubed. That square root I just worked out as secant. I have a 2 dx becomes secant squared theta d theta. So I think this is all turning into 1/16 integral of tangent cubed theta secant theta d theta. Is this the bad one? Here's what I'm thinking in my head about the good bad one. The bad one is the integral of secant cubed. I don't like it when there's an even number of tangents and an odd number of secants. I don't have that here. I have the odd number of secants, but I have an odd number of tangents. An odd number of tangents is supposed to be good. Why would an odd number of tangents have been good? What was that all about? Oh yeah, because I can pull out a tangent and a secant. Like one tangent left over can get pulled out to the end with a secant, and that looks like the derivative of something. What u substitution is this begging me to do? I want u to be secant theta. Aha, if u is secant theta, then I want this to be only secants, and I can make a tangent squared into a secant. How does that work? Tangent squared is secant squared minus 1. I totally knew that right off the top of my head. So this becomes 1/16 integral of u squared minus 1 du. That's going to be 1/16 1/3 u cubed minus u. I guess I'll push the 1/16 in. This is 1/48 u cubed. U was secant, secant cubed, minus 1/16. I said 48, but I wrote 14. That should be 1/48 secant cubed, minus 1/16. U is secant. We undid one of the substitutions, but not the other one. The other substitution was 2x equals tangent theta. Okay, we gotta draw a reference triangle. Tangent theta is 2x. So opposite over adjacent is 2x over 1. So this is the square root of 4x squared plus 1. So cosine theta is adjacent over hypotenuse is 1 over square root 4x squared plus 1. So secant theta is square root 4x squared plus 1. So this is... So our answer is 1/48. Secant cubed is that to the 3/2 minus 1/16. Secant theta is that to the 1/2. Booyakasha. What's up next? Seven. Let's do 8 and 9. Integral of cosine 1 minus x cubed. I don't know how to do this one. This is the non-elementary one. I actually don't know that it is non-elementary, but I don't know how to do it, so this is the one that you're not expected to know how to do. Number 9, we're integrating sine squared, cosine squared. These are even powers of sine and cosine. If either of these was odd, we'd be in a good place to do a u substitution. They're both even. This is where we have to do those identities. They change them into that reduce the power. Sine squared is 1/2 1 minus cosine 2x. Cosine squared is the same thing with a plus. You can get these from the double angle formulas for cosine 2x. That's the weird one where there are 3 of them. So if I FOIL this out, first off, let's pull the halves outside as a fourth. I get 1 minus cosine 2x, 1 plus cosine 2x. That's a difference of squares. The cross terms will cancel. This is 1 minus cosine squared 2x. I know how to integrate the 1. This is another cosine squared. How do I do cosine squared? Well, cosine squared something is 1 plus cosine double that thing over 2. Cosine squared x becomes 1 plus cosine 2x. So cosine 2x is going to become 1 plus cosine 2x. We call that 4x. If I split this into separate fractions, so I could integrate the 1, and it feels good to integrate the 1 right now, but if you've done these problems before, you know it's going to be 1 minus a half cosine 4x. You can combine these two together, and then you're only integrating 1, 1. Not like it's hard to integrate 1. Having to integrate it twice isn't bad. I'm integrating half minus half cosine 4x dx. Let's go ahead and push that in. So these become eighths. I get 1/8 x minus integral of cosine 4x is sine 4x divided by 4. If you did this a different way than me, that is totally fine. There are many ways to do most of these problems. A lot of these I like putting on exams specifically because there's many ways to do them. Integrating x arctangent x. How do we do that? This is definitely a parts problem. This is that Lyautey thing. We really like letting inverse trig functions, their derivatives aren't inverse trig functions anymore, and parts is the way I can change an arctan into its derivative. So let's let u be arctan x. dv is going to be everything else. du is the derivative of this, 1 over x squared plus 1. v is going to be the integral of that, half x squared. So number 10, the integral, let's write the 10, the integral of x tangent inverse x dx is uv half x squared tangent inverse x minus the integral of v du is 1/2 x squared over x squared plus 1. How do you integrate x squared over x squared plus 1? Why is that tricky? That shouldn't be hard. At the very core, that's a polynomial over a polynomial. You should be able to recognize this is a rational function, so the stuff I learned about partial fractions should be relevant here, even if the bottom doesn't factor at all. Like, the lessons of partial fractions still apply. And the first lesson was do long division if you have to. The top is not smaller than the bottom. That's part of what makes this tricky. Let's do the long division. I need x squared divided by x squared plus 1. That goes in once. Subtract, you get a remainder of -1. I can rewrite x squared over x squared plus 1 as 1 minus 1 over x squared plus 1. You can get there faster if you write x squared over x squared plus 1. If you put a plus 1 minus 1, you can see, oh, that part makes a 1, and you're left with that, and then you know how to integrate both of those. You get stuff minus 1/2 the integral of 1 minus 1 over x squared plus 1. Integral of 1 is x, so I get minus half x. Integral of that is arctangent. -1/2 of minus arctangent makes plus 1/2 arctangent. What was that first stuff? That first stuff was half x squared arctangent. Weird that we got arctangent on both ends. Maybe that's not weird. Next up, 1 over x root 16 minus x squared. Is there... It's obviously wanting a trig substitution. I think a little bit, is there a u substitution that does it faster? There's no extra x floating outside, or not on top where it could mesh with the dx, so not obviously a good u substitution. Let's try the trig substitution. I want x to be 4 sine theta. dx is 4 cosine theta. I like x equals 4 sine theta because then x squared is 16 sine squared theta, and 16 minus x squared is 16 minus 16x squared is 16 1 minus sine squared. That's 16 cosine squared. And the square root of that is 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 4 cosine theta, with an absolute value that I'm not dealing with. So my integral turns into 1 over x is 4 sine theta. That square root we just said was 4 cosine theta. dx is 4 cosine theta. 4, 4, cosine, cosine. I'm left integrating 1/4. 1 over sine is cosecant theta. Ooh, I hope I know the integral of cosecant theta. I can. The reason... The way to get there by itself is multiply this by cosecant plus cotangent over cosecant plus cotangent. Or you can do an obnoxious substitution that leads to a whatever. When I was taking this exam, I found it worthwhile to memorize it, and I kind of recommend you do too. The integral of cosecant is negative natural log absolute value, cosecant plus cotangent. For secant, it's natural log absolute value, secant plus tangent. For cosecant, it's natural log absolute value, cosecant plus cotangent, and it's negative. Oh, I gotta undo the trig substitution. Don't put a box around that. Dang. This problem was about x's. I can't give them an answer about thetas. How do I change this back? We started with sine theta was x over 4. So that's... Here's a triangle where sine theta, opposite over hypotenuse, is x over 4. So this is the square root of 16 minus x squared, if I use the Pythagorean theorem. If sine theta is that, then cosecant is 1 over sine. Sine was x over 4, so cosecant is 4 over x. What's cotangent? Tangent is opposite over adjacent, so cotangent is adjacent over opposite, is square root 16 minus x squared over opposite is x. There's our answer. Gross answer. Whew. Are we almost done? Wait, why am I scrolling up? It's not over there, it's over here. We are almost done. X squared cosine x. This is the kind that's well suited for tabular integration. If you're not doing tabular integration, be prepared to do integration by parts twice pretty quickly. Tabular can save you a bunch of time. X squared, derivative of that is 2x, derivative of that is 2, derivative of that is 0. Cosine 2x. Integral of that is half sine 2x. Integral of that is negative a fourth cosine 2x. Integral of that is negative an eighth sine 2x. I need positive, negative, positive of that. So the integral of this is positive the first is half x squared sine 2x. Negative the second, that one has a minus sign on it. The minus that comes from, like, you're alternating in tabular integration. So this minus and that minus cancel each other. This comes out being positive. 2 over 4 is a half x cosine 2x. The last one is positive, with that negative makes it minus. 2 over 8 is a fourth sine 2x plus c. Cool. Secant cubed, tangent cubed. Ooh, the hard... I'm going to go through the same reasoning I had a second ago. Integrating secant cubed is hard. The hard version is when there's an odd number of secants and an even number of tangents. Good news for us, this is not the hard version, because we have an odd number of tangents. Why was that good? That's right, I can pull out a tangent with the dx. I also want a secant with that, because that's what makes it the derivative of something. So I'm left over here with secant squared, tangent squared. Writing the secant squared tangent squared over... The secant tangent here is telling me what u substitution I want to use. U is secant x is the thing where du is secant tangent. If u is secant, then I want this stuff to be only secants. This stuff is already secants. I need to convert the tangent squared. How do I convert tangent squared? Sine squared plus cosine squared is 1. Sine squared over cosine squared plus cosine squared over cosine squared is going to be 1 over cosine squared. That says tangent squared plus 1 is secant squared. Okay, tangent squared is secant squared minus 1. This u substitution turns this into the integral of u squared minus 1. I've seen du. I've seen so many calculus students get to this point and fumble. This is a polynomial. Foil it out. It's not that bad to foil this out. We're integrating u to the 4th minus u squared. It's just the power rule. This was day 1 of integration. 1/5 u to the 5th minus 1/3 u cubed. What was u? U was secant theta. 1/5 secant to the 5th theta minus 1/3. No, it wasn't theta, it was x. 1/5 secant to the 5th x minus 1/3 secant cubed x plus a constant. We're close. 14. Hint, check problem 2. I'm likely to do this on yours also. Number 2 was just find the partial fraction expansion, and I didn't make you integrate it. 14 says, well, now integrate that thing. The partial fraction decomposition will probably be useful. You don't have to redo the partial fraction thing. I had a couple students do that before. You can just copy the work over. Where did I do that work? Let's grab this. Copy. This is not the end of the problem now. This is the beginning of the problem. So the integral of this, I've already worked out, is the integral of this. I know how to integrate this. This one is a little trickier. I'm going to split it up into two things. Actually, I'm going to split it up into separate integrals. Minus 4/5 integral of x over x squared plus 4 dx minus 3/5 integral 1 over x squared plus 4 dx. How cheaty do I want to be? This one I know. 4/5 natural log absolute value x minus 2. This one is begging for the substitution u equals x squared plus 4. du is 2x dx. It turns into 2/5 integral 2x. We get the integral of du over u is natural log absolute value u. So this answer is 2/5 natural log absolute value x squared plus 4. If you were doing a calculus book and you checked your answer, they wouldn't have the absolute value. And the reason they're getting rid of the absolute value, like you need an absolute value when you integrate 1 over x, but x squared plus 4 is positive, so its absolute value doesn't matter. Minus, what's 3/5 of the integral of that? You want to either be good enough at doing the trig substitution fast. The trig substitution would be x equals 2 tangent theta. X squared plus 4 is going to be 2 4 secant squared theta. But dx is also 4 secant squared theta. So you're going to be integrating 1, which will be theta. So your answer will be, there's going to be an extra half out there from something. Oh no, dx is 2 secant squared theta. That's where the extra 1/2 comes from. You end up with 3/5 of 1/2 tangent inverse x over 2. I think it's... I don't know why I know this, but the integral of 1 over x squared plus a squared is almost tangent inverse. The answer turns out to be 1 over a tangent inverse x over a. That's one of the things I left Cal 2 having memorized. I don't know if that one's worth memorizing, because the trig substitution is kind of doable in 3 or 4 lines. It's one that I had memorized. I don't know there's corresponding things for sine inverse and secant inverse where... I mean, really, what you got to know is what is the right constant out front. That's this exam. I think I just did it in an hour, and I didn't skip the problem I'm allowed to skip. You guys are getting 2 hours. Actually, let's make it 2.5 hours. This stuff is rough. I'll go put that on the instructions page. I'm also going to rewrite the instructions page for the practice exam to show you what the instructions will be on your practice exam, because I don't want there to be surprises. There's a little more I want to write because it's a take-home. I'm done talking. I'm not planning on lecturing tomorrow, but you're welcome to text me with questions. I'm getting paid to answer your questions. Show me what you got. Monday will be the exam. Tuesday I'll be lecturing about sequences and series, our next big topic. I don't know if all of the exams graded by Tuesday. I guess we'll find out. Do you want to hear a joke? Is anybody watching me? Telling a joke on a live stream is the worst. Telling a joke and not hearing people laugh crushes my soul. I'll save the joke for later. I'll talk to you guys later.